All right, so this is the 23rd class for probability. And what we're going to do today is we're going to talk about more things on the chi-squared distribution. And again, we're going to do integrating without integrating, but we will also do integrating with integrating to really drive home why it's so much nicer to be able to step back and really see what's going on. What's lurking is the theory of the normalization constant. If you have a probability distribution, what must it integrate to? 1. So if you can get the functional form, and you can say, well, hey, this has the same functional form as the normal, except there's this strange constant outside. Well, then the only possibility for that strange constant is the normalization constant of the normal. Or if it looks like an exponential except for a strange constant, or a chi-squared except for a strange constant, you can then figure out what that constant is without doing all the intervening steps. As a nice aside, we might actually be able to prove today the surface area of the n-dimensional sphere, or the volume of the n-dimensional sphere. And there are a lot of nice applications of stuff like this. All right, so the chi-squared distribution has, with new degrees of freedom, you always have to specify the number of degrees of freedom, is 2 to the minus nu halves, gamma nu halves inverse, x to the nu halves minus 1, e to the negative x halves. And this will be x greater than or equal to 0. And this is very similar to the gamma function, which is defined, gamma of s is the integral of x to the s minus 1, e to the minus x. The difference is, of course, is this has an x over 2, this has an x. Depending on the problem you're looking at, one is more natural than the other. We know gamma of n plus 1 is n factorial, and we know if x is normal 0, 1, then x squared is a chi-squared random variable with 1 degree of freedom. We proved that last time. This is one of the reasons why it's so important. By the theory of grouping, we want to be able to show that if we can calculate the distribution of sums of chi-squareds, well, to do that, we really only have to deal with the sum of 2 chi-squared random variables. If the sum of 2 chi-squared random variables is a chi-squared random variable with the degree of freedoms equal to the degree of freedoms, the sum of the degree of freedoms, we're done by grouping. And we just march down the line as we did with normals. So what we really want to do is we want to add 2 chi-squared distributions, one with nu 1 degrees of freedom, one with nu 2 degrees of freedom, and show that it's equal to nu 1 plus nu 2. It turns out if we have variables that have just 1 degree of freedom, the calculations are a little bit easier. We cannot stay with 1 degree of freedom because as we keep adding, the degrees of freedom increase. But let's just look at that one special case. So let's consider x1, x2 are both normal 0, 1 and independent. We're going to study x1 squared plus x2 squared. And we'll call that y. So really this is the same as adding 2 chi-squared degrees of freedom with chi-squared random variables with 1 degree of freedom. There's a lot of different approaches we have. One of the big approaches we have is the CDF method, where we write down a convolution integral and we evaluate the integral. Another one, instead of the convolution approach, is the CDF approach. Let's do the CDF approach. Let's look at the cumulative distribution function of y. So this is the probability that big Y is at most little y. So this is the probability of x1 squared plus x2 squared is less than or equal to 1. Now I could convert x1 and x2 to chi-squared random variables. There's probably a reason I'm writing it like this. I really like seeing something like x1 squared plus x2 squared is less than or equal to, oh sorry, this is a y. Less than or equal to y. What does this look like geometrically? A circle. So it's basically saying, what's the probability that x1 squared plus x2 squared is less than or equal to y? What's the probability we're inside a circle of radius square root of y? So what we would want to do there is we would get fy of y is just the integral x1 squared plus x2 squared is less than or equal to 1. And now I have the density, but my densities are the densities of normals. So I have 1 over square root of 2 pi e to the negative x1 squared over 2, 1 over square root of 2 pi e to the negative x2 squared over 2 dx1 dx2. If you listen very carefully, you can hear this screaming at you. Right? If you remember your Calc 3 days, what is this screaming at you to do? Yes? Convert to polar. We see that we're integrating over a circle. As soon as you see you're integrating over a circle, your thought should be, let me convert this to polar coordinates. We really don't do that much in Calc 3. We know how to switch orders of integration, and we know how to change variables. So the question is, which would you rather have? A nasty integrand over a nice region, or a nice integrand over a nasty region? Frequently, we prefer the nicer region. What does a circle look like in polar coordinates? Well, geometrically, in polar coordinates, if I were to write a circle, here's theta, here's r. What does a circle look like in polar coordinates? Yes?
Just like a given value of r?
Well, here it's, oh, this should be, I keep dropping the y. So,
R is equal to y?
so here, right. So here we're actually doing square root of y. This is what the circle would be. In polar coordinates, the circle is just a rectangle. We love integrating over rectangles. These are nice regions. So in polar coordinates, we get 1 over 2 pi. Now we have the integral, say theta goes from 0 to 2 pi. Integral r goes from 0 to square root of y. Now we have e to the negative x1 squared plus x2 squared. Oh, that's e to the negative r squared over 2 r dr d theta. The theta integral is easy to do, so we'll do it. That gives us 2 pi, which cancels with the 2 pi out there. And in the r integral, oh, look at how nice that is. Right? We have an e to the minus r squared over 2. The derivative of that is negative r. So we're going to just flip the order. So we'll get e to the negative r squared over 2, flipping the order, and we get 0 and square root of y. So we get 1 minus e to the negative y over 2. And what must be true about y for this problem? So what's true about y for this problem? Yes? Y is greater than or equal to 0. Why does it have to be greater than or equal to 0? I'm sorry? Yeah, it's a square. I want x1 squared plus x2 squared to be less than or equal to y. If I'm going to be using this, y is my radius. My radius has to be a positive number. So I now have the formula for the cumulative distribution function of y. I can get the density by just taking the derivative. And so I get little fy of y. The negative cancels, and we'll get 1/2 e to the minus y over 2 if y is greater than or equal to 0, 0 otherwise. This distribution has 2 different names. Somebody give me one name for this distribution.
It's a chi-squared distribution with 2 degrees of freedom.
So one is it's chi-squared with 2 degrees of freedom. What's its other name? Other name is exponential. This is wonderful. So the exponential actually sits inside the chi-squared family. Now, here's where things get interesting. What if instead of doing a sum of 2 normals, what if I did a sum of n squares of normals? So this is where I strongly urge you not to be writing things down. It's all in the book. This is the advantage of doing things on the blackboard. Okay? So I'm going to just try to do this somewhat fast on the blackboard. Try to enjoy the show. The details are in the book. So let's do x1 dot 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 xn on normal 0, 1. So now plus dot 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 xn squared equals y. So this is now just x1 plus dot 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 plus xn squared is less than equal to y. So far, so good. Right? This is the advantage of being at the blackboard with chalk. All right. Now I come over here. Now things become a little bit harder. So I'll have x1 plus dot 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 plus xn squared. And I'll have here times dot 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 times 1 over square root of 2 pi xn squared dx1 dot 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 dxn. All right. And at this time, I'm going to have to now start doing some work again. OK. It's time to play What Did You Do in Calc 3? Who remembers the change of variables for spherical coordinates? This is where you have products of sines and cosines, and one of the angles goes from 0 to 2 pi, and the other angle only goes from 0 to pi. Right? People vaguely remember this, or they at least remember that something like this was done. How many of you have seen the change of variables for 4 dimensions for the sphere, the fourth sphere, the n sphere? Right, not that many. That's what we need now. We need the multi-dimensional change of variable formula, and we need to write down what all the variables are. So we're going to have r and then theta 1. How many angles will we have? Yes. We'll have n minus 1 angles. So what you have to do is you have to write down the determinant of the Jacobian of the change of variable. How many of you vaguely remember stuff like this? This sounds like a very painful Halloween lecture, right? I don't want to go through the details of that. It's in the book. I want to just big picture. In polar, we went from dx dy to r dr d theta. And I told you that in polar, we should really view it as dr times r d theta, because that's what gives us the length. Really, there's something else going on here. There's a function of r and theta here. And that function just happens to be identically 1. We have a change of variable here. What's going on here? dx1 through dxn goes to dr d theta 1 d theta n minus 1. What is the r dependence? I need this to be a volume. What's the r dependence? R to the n minus 1. Right? This is already in meters. These are not numbers yet. These are not units yet of length. I need to multiply each one of these by an r. So I have an r to the n minus 1. And then I have some function h of theta 1, theta n minus 1. How many of you remember what that is in spherical? I think we often use rho in math classes. You'll have rho squared d rho d theta d phi. And it's either like a sine squared phi or a sine squared theta, depending on which way you choose your variables. Does that sound vaguely familiar? That there's something involving a sine squared? We now need the n-dimensional generalization of this. Okay? The point of today is to show you that you do not. Let's look and see what happens. So we get fy of y is the integral. I'll do it this way. R is going to go from 0 to what? What does my radius go up to? Square root of y. And I've got theta stuff. If this wasn't recording, I would have used a different word beginning with s. Something for theta. Okay? I don't really care. I'm going to get some constant. I'm going to get 1 over, I'll get 2 pi to the negative n halves. I will get e to the negative r squared over 2. And then what comes next? I'll have this h of theta 1, theta n minus 1, d theta 1, d theta n minus 1 times r to the n minus 1 dr. Everybody comfortable that I get something like this? Would you rather do the r integral or the theta integrals? I'm sorry? I can't hear you. It's the first one, the r integral? Okay. This is in fact the same, almost the same as what we had before. So we will have, this is equal to 2 pi to the negative n halves. The integral r goes from 0 to square root of y, r to the n minus 1, e to the negative r squared over 2 dr. And now we have all the theta integrals. What can you tell me about all the theta integrals? Yes?
Well, there isn't any R dependence.
There's no R dependence, but more important than no R dependence is no... What's the other letter we care about right now? Not just R. Yes? Well, there's theta dependence in the integrand, but when we do the theta integral, there's no R dependence, and there's no what else? What does this integral depend on? Y. There's no y dependence. It's just some integral. It's a number. Let's give the number a name. C sub n. Not surprising that that integral should depend on n. But it will have no y dependence. It will have no r dependence. It's just a constant. Okay? Any questions about this? This constant is going to be related to the surface area of the n-dimensional sphere. And so I'm probably not going to go through this in class. It's in the book. And if anybody wants to, I'm happy to talk about it in office hours. If there's a huge groundswell of people who want the details in class, just email me and we'll do it in class. I'm trying to balance how much theory to give. So I want to give enough so that you can then read if you're interested, but not so much that if you don't give you're bored to death. Okay? Who knows how to handle the r integral? Anybody know the antiderivative of r to the n minus 1 e to the minus r squared over 2? Yes? So we could try doing it by parts, and we have an r squared, so we probably want to include an r over there. One possibility is to do it by parts, and that will work. There's a better way. Do we care what the antiderivative of this is? What are we going to do as soon as we calculate the antiderivative of this? We're going to take the derivative. Why calculate explicitly the antiderivative only to then immediately take the antiderivative? Right? We're just going to come back to where we started. So we need a letter. Big R be the antiderivative of the R integration. So then we'll get big Fy of y is equal to 2 pi to the negative n halves Cn. And then we will have the antiderivative I'm calling it r. The antiderivative at square root of y minus the antiderivative at 0. So now if I want to get the density, I just take the derivative. And I'll get 2 pi to the minus n halves Cn, and the derivative of r is just going to be my function here, evaluate its square root of y, but then I also have to take the derivative of square root of y. So I would now get y to the n minus 1 over 2 e to the negative y over 2. And now I have to take the derivative of y to the 1/2, which will then just be 1/2 y to the minus 1/2. So collecting everything, I have some constant, I'll call it Cn tilde, y to the n over 2 minus 1, minus a half is minus 1, e to the negative y over 2. If I have done things correctly, so if I've done things correctly, I have not erased everything I need from the board. And we should be able to come back over here and look and see what's going on. Here is the density for the chi-squared distribution. So we can come back. No, we're not. So we can come back and look and see what is the density of a chi-squared distribution. Does what we have look like a chi-squared distribution? Which chi-squared distribution does it look like? Yes?
There are, I guess, n degrees of freedom.
Yeah, it looks like a chi-squared distribution with n degrees of freedom. The only thing it's got the same functional form. I'm using the letter y instead of the letter x, not a big deal. But I don't have the right normalization constant. Or actually I do, but I just don't know that I do. This is a probability distribution. It has to integrate to 1. So Cn tilde has to be whatever's required so that when I integrate this, y goes from 0 to infinity, I get 1. I already know what I need to make this integrand integrate to 1. It's this piece. Therefore, the theory of normalization constant gives us Cn tilde is 2 to the negative n halves gamma of n halves to the minus 1. And we're done. So this is the power of normalization constants. Okay? I absolutely love this subject. To me, I think it's phenomenal how well it works. How many difficult integrations it allows us to bypass. We do not need the n-dimensional spherical change of variables. And if you want, you can actually now use this to get the surface area of the n-dimensional sphere or the volume of the n-sphere if you want. What's the area of a circle? Radius r. It should not take this long. Area of a circle of radius r. Pi r squared. What's the perimeter? 2 pi r, the derivative. What's the volume of a sphere of radius r? 4/3 pi r cubed. What's the surface area? 4 pi r squared. Think about the connections as to why is one the derivative of the other. You can use this to pass from the surface area to the volume or the volume to the surface area. We can now use this to get. There's so much going on here. One of the other things that's worth knowing is what constant surfaces in these formulas for perimeters and volumes and areas of spheres. What's the big constant? Pi. If you look at the gamma function, gamma of 1/2 is the square root of pi. The gamma function is floating on in all of this stuff. That's where things are coming from. So if you look at what kind of pi's and what kind of normalization constants in front do you have, it's all related to the gamma function. So there is a wealth of stuff going on here. So this is enough to prove that the sum of n chi-squared random variables, each with 1 degree of freedom, is a chi-squared with n degrees of freedom. It gives us surface areas and volumes of spheres, and it shows us that we do not actually have to calculate these change of variables. Okay. Any questions about this? Unfortunately, this is not enough to handle a general sum of chi-squared random variables. This only works if the chi-squared random variables are integers. So if I have a sum of a chi-squared random variable with 5 degrees of freedom and 4 degrees of freedom, I can expand each one up. So now I have a sum of 9 chi-squared random variables with 1 degree of freedom, and I can handle that. So as long as my chi-squared random variables have an integral number of degrees of freedom, we're OK. How many of you are taking stats classes or have taken stats classes with chi-squared random variables? Have you ever seen a chi-squared with non-integral degrees of freedom? Okay, so the statistician is, I'm not really seeing it, I'm not really that worried. Okay? If you're doing things in terms of data analysis, if you're going to be summing squares of normals, everything is going to be integral. But you could also use a chi-square distribution to model a phenomena. You know, we saw when we were looking at the Weibull distribution and sabermetrics last time that it was useful to have these free parameters gamma. Gamma doesn't have to be an integer. If gamma was 1 or 2, the shapes were nice, the distributions were nice, but we can handle things in greater generality. So what I want to do now is I want to do the final case of just a sum of two arbitrary chi-squared random variables. And it will be another way of integrating without integrating. It'll also allow us to deal with one of the most common mistakes people make when they deal with convolutions. So let's say xi is chi-squared with nu I degrees of freedom, and they're independent. And we'll let y be x1 plus x2. So we know the density of y is the integral from minus infinity to infinity of f nu 1 of t, f nu 2 of x, I guess we're doing y, of y minus t dt. Okay? So these are the densities of my chi-squared random variables. Now initially the integral goes from minus infinity to infinity, but because of the chi-squared density over here, I can restrict the integration a little bit. What does this allow me to restrict the integration to? The first one over here. Yes? 0 to infinity. Because the chi-squared random variable vanishes, the density vanishes at negative inputs. What about the second one? What does that restrict the integration to? I'll let Becky. Yeah. I'm sorry? Well, y is fixed. It's t is the variable. Okay, so it goes to y. So this is the same as integrating from 0 to y of f nu 1 of t, f nu 2 of y minus t dt. We can't use, we now want to substitute in what these densities actually are. Okay? And because the densities are 0, if we don't have a non-negative input, we can restrict the integration. Okay. So now let's continue, and we get fy of y. I'm going to call the normalization constants c nu 1, c nu 2, in obvious notation. Okay. So it'll be c nu 1, c nu 2, integral from 0 to y. And then the first one's density is going to be t to the nu 1 over 2 minus 1, e to the minus t over 2. And the next one will be y minus t to the nu 2 over 2 minus 1, e to the minus y minus t over 2 dt. And again, all of this algebra is in the book. If you want to just watch what's going on now and not write it down, that's fine. Well, when we see this, some of the things combine. We have an e to the minus t halves, and over here we have an e to the plus t halves. So those combine and become just 1. We're left with an e to the minus y over 2, but y has no t dependence, so we can pull it outside the integration. And so we get this as c nu 1, c nu 2, e to the negative y halves, integral from 0 to y of t to the nu 1 over 2 minus 1, y minus t to the nu 2 over 2 minus 1 dt. Is this an easy integral to evaluate? Probably not. With the news. Now, it turns out that this is related to a beta distribution, which is related to product of gamma distributions. There are ways to evaluate this. Do we need to evaluate this carefully? Do we need the exact answer? Or what do we really only care about? What do we care about for this integral? Yes? Well, we know when we integrate them with respect to y, it will integrate to 1. So we care about something about this part in here. I don't need to evaluate it completely. Yes?
You only need to evaluate anything that's going to give you a y?
I only need to find the y dependence. I can't do the trick we did a moment ago where we just take the derivative and say, screw the integration, because we're not taking a derivative anymore. This is the density. I only need to find the y dependence. What would you love to replace t with? Y. Well, you can't just change t to y, but we could let t equal y times u. And then dt would equal y du. And now we get that this equals c nu 1, c nu 2, e to the negative y halves integral. All right, so if t goes from 0 to y, what does u go from? So what does u go up to? 1. Oh, that's nice. Right? No more y dependence in the integration. Now this over here, I'm going to get a y to the new 1 over 2 minus 1. And I'm going to write the other term here, u to the new 1 over 2 minus 1. I'm just going to split this up into two parts. This part over here, when I replace t with yu, I can now pull a y outside this. I'll get y to the new 2 over 2 minus 1. And then over here, I'll get 1 minus u, new 2 over 2 minus 1. And then dt becomes y du. Let's put the y over here. Now let's pull the y outside the integration. And we get c nu 1, c nu 2, e to the negative y halves, y to the new 1 plus new 2 over 2, minus 1 plus 1 is minus 1, integral from 0 to 1 of u to the new 1 over 2 minus 1, 1 minus u to the new 2 over 2 minus 1, oh, this is not dy, this is du, du. What can you tell me about this integral? Yes?
Well, I know that there's not going to be a y in it.
There's no y in it. So what we get is it equals y to the new 1 plus new 2 over 2 minus 1 e to the negative y over 2 times c nu 1, c nu 2. Let's call it c tilde nu 1, nu 2. Because this integral will depend on nu 1 and nu 2. What does this look like? This is tough to give as a Vulcan and trying to stay dispassionate. What does that look like? What density? Chi squared with nu 1 plus nu 2 degrees of freedom. And in fact, you can now use that to figure out what this integral is. So this is another way of calculating integrals for the beta distribution, is we recognize that it's coming as the normalization constant of a chi squared. So this is very different than what you've done in Calc 2. You know, in Calc 2, they actually cared about you integrating and solving the problem. I only care about getting partial solutions. And we can correct because we know it has to integrate to 1. So once we can sniff out the y dependence, we're done. So this is an extremely powerful technique. This is why it was worth spending as much time as we did on this. Because integration is hard. And this is giving us ways to bypass. It's also giving us results we care about. You know, surface area of spheres, volumes of spheres. These are things that are quite important. Okay, so if you smile at this, you are both human and probably a potential math major, if not an actual math major. If you are not really that excited about this, math major might not be for you. You might want to consider something else, or stay away from analysis. You know, try algebra, try geometry. This bypasses so much horrendous algebra, so much horrendous calculus. Okay. Any questions on this? So I'm not going to do more problems along these lines. This is, I think, enough of integrating without integration. Okay. What I want to do now is I want to shift to a completely new topic. So we've just finished a major section of the book. We're now shifting to limit theorems. And the first idea is we want to try to estimate various probabilities. Not surprisingly, the more information we know, the better we should be able to do at estimating probabilities. Okay? Let's say I tell you x is a random variable. And I want to calculate what is the probability that x is greater than or equal to a. What can you give me? Yes? It's between 0 and 1. You really can't do much more if all I've told you is I have some random variable. So the question is, as I provide more information about this random variable, maybe we can refine our estimate. What one piece of information would you like to know? That's more than one piece of information. That's infinitely many pieces of information. I'll give you one number. Wait. You want to refine yours? I'll give you one number. But you want to do this for every a. I'm going to keep changing the a. So if there's one number that I can associate to a random variable x, what one would you like to know? The mean. Right? If I can give you one piece of information, let's take the mean. So assume we know the expected value of x. Not all distributions have a mean, but let's assume we have a distribution that has a mean. And without loss of generality, what can we assume the mean is? 0. I'm worried that I'm probably not going to be able to say anything meaningful because I can always shift the mean to be 0. But what can we estimate for this probability? We know it's between 0 and 1. Can we do anything better? Yes?
If a is less than 0, we know it's between 0 and 1.5. And if it's greater than 0,
we don't know the distribution is symmetric.
Oh, right.
So if we knew symmetric, that would be very different. So always look at extreme cases. Here's the mean. One possibility is I could put almost all of my probability just a little bit to the right of 0. And a very small probability, very negative. What would the mean of this be? 0. If I choose this appropriately, I could have the mean 0. And so if a is just a little bit above 0, I can actually set it up so that this probability is 0. Right? I could also do it the other way. And then the probability would be, I can basically get this to be anywhere between 0 and 1 by playing with these extreme cases. So extreme cases cannot do well. I could consider a distribution where almost all of my probability is just a little bit greater than a. And then I would have a very small negative probability very far down so that the mean would be 0. And then I would have almost 100%. So I can basically get this as close to 100% as I want. I can get it as close to 0 as I want, depending on the distribution. So if all you know is the mean, we really can't do anything well. So what we're going to do is we're going to get up to Markov's inequality. And the point is I want you to see that the assumptions we make are reasonable assumptions. These are assumptions that will give us a chance of getting a result that can be of use. If we just assume the existence of the mean, it's going to be hard to get anything that will be valuable. So now we want to assume something about the shape of the distribution. So we had one suggestion was that let's assume that the distribution is symmetric. That's one way you can go. Another assumption people make is assume that a random variable is greater than or equal to 0. Okay? And we'll assume that the expected value is finite. What can we say in this case? Well, if a is less than 0, it's trivial. What's the probability if a is less than 0? It'll just be 0. So the interesting case is when a is greater than or equal to 0. What do you think the natural units are to measure a in? So you always want to ask, what are the units for the problem? What's the correct scale? We don't necessarily have a standard deviation, right? The standard deviation would be assuming the second moment exists. I could give you a density such as some constant over 1 plus absolute value of x cubed. This will have a mean of 0, but it will not have a variance. So you can't measure it in terms of the standard deviation. Yes?
Measure it in terms of the mean?
In terms of the mean. That's the only thing that we have. So basically you could say, is a twice the mean? Is a half the mean? Is a 3/4 the mean? The natural quantity is to look at a relative to the mean. So the probability that x is greater than or equal to a is the integral from a to infinity of the probability density of x dx. Okay? So we have the following integral. We don't know what the density f is. We're going to be able to get an upper bound for this. So this will be less than or equal to an integral from a to infinity of fx of x dx. What I want to do is I want to try to motivate why we're about to do what we're about to do. I can easily write down what comes next. It's logical. There's only one thing to write down. I want you to see why it's logical. What's the one quantity we are given any information about in this problem? What are we told we know? I'm sorry? E of x, the mean. So what integral is related to this that has a mean in it? What should we throw in here? We throw in an x. Now, you can't just multiply by x. But what if we multiply by x over a? How does x over a compare to 1? Well, x is going from a to infinity, so x over a is always at least 1. And that's why we have a less than or equal to here. And now if I just pull out the a, this is looking a lot like the mean. So the idea is we want to somehow work the mean into what we're doing. If x goes from a to infinity, then x over a is always greater than or equal to 1. So this is only going to make the bound larger. So then we would get that this is equal to 1 over a, the integral from a to infinity of x fx of x dx, which is less than or equal to the expected value of x over a. Because the expected value, we would be integrating from 0 to infinity. We're integrating from a to infinity. I will let you go through this carefully and see where are we using that the random variable x is non-negative. But this gives us Markov's inequality, that the probability that a non-negative random variable with finite mean is at least a is equal to, at most, the expected value of x over a. So as a gets larger, the probability gets smaller, and it gives you some idea of the rate. What we would often do is we might take a to be maybe L times the mean. So what's the probability you're L times the mean? It's at most 1 over L. This is not a great result. 1 over a, 1 over L, it's decaying slowly. Why is this such a bad result? Why is this doing such a bad job?
Because we have so little.
We have so little information. I am trying to prove a result here that holds no matter what probability distribution you give me, so long as it has some mean and it's non-negative. That describes too many things. The reason this sucks is because it's trying to do too much. if we knew something about the shape of the distribution, we should be able to do better. What would you love to know about the distribution that's already been remarked? You'd love to know the variance. And so if you know the variance, you can do better. And so the next step is to assume we know something about the variance. And so I will just explicitly write this down because this is Markov's inequality. So the probability that x is greater than or equal to a is less than or equal to the expected value of x divided by a if x is greater than or equal to 0. Do I need to assume that I have a finite mean for Markov? No, it still holds. It's useless, right? The probability is at most positive infinity. Okay? It's not an incorrect result. It's just not a result to be proud of. Okay? So probably my favorite mathematician is Chebyshev. How many of you have heard of Chebyshev? What I love about him is no matter how you spell his name, it's correct. He has more conversions of his name from Russian to English than anyone else. What I have been trying for years to do but have not succeeded is to convince people to spell his name differently for different theorems of his. So when you say Chebyshev's theorem, depending on how you spell it, you would know exactly which theorem you're talking about. I think this is the one I like the most, with a C, then an S with a V at the end, not two F's. That's just wrong. Chebyshev's inequality. So let's say x has finite mean and variance. Then the probability that x minus mu is greater than or equal to k sigma is less than or equal to 1 over k squared. If you look at this, we are doing everything the right way. We're looking at how far x is from its expected value. How far is it from the mean? What is the fluctuations about the mean? What scale should we use to study things? We should use the standard deviation. How many standard deviations away is it? And what this is saying is that the probability is decaying like 1 over k squared. Okay? There's two ways to prove this. One way is to go through and do the algebra very similar to this. And then what you would do, proof 1, is you would use 1 is less than or equal to x minus mu over sigma, I think, squared, if x minus mu is greater than or equal to, let me just do it right. I want to do it like this. Okay. So if x minus mu is greater than or equal to k sigma, then k squared is less than or equal to x minus mu squared over sigma squared. And then we do an exact same argument like this, and we'll have a variance coming out. Another proof, proof 2, is let y equal x minus mu squared. What's the expected value of y? So if y is x minus mu squared, what's the expected value of y? I'm sorry? The variance. Excellent. Sigma squared. What should we now apply? Foreshadowing is the art of a great lecture. Apply Markov. What does Markov need? Markov needs a non-negative random variable with finite mean. Here is a non-negative random variable with finite mean. So that's another way of proving it. Is if we know Markov, we get Chebyshev immediately. But the advantage of Chebyshev is that now, if we have a variance, we can use that variance to look at things on the right scale, not just copying about multiples of the mean away, but looking at the right units. All right, so this is a good place to stop. Feel free to grab candy. Okay.